Hi, welcome back. We're now going to look at a few ways you can collect and secure data. In this section, we'll explore some of the techniques and challenges associated with collecting and securing the data that's needed for machine learning. Consider again the original example about predicting credit card fraud. You've further formulated the problem. But what data do you need to actually train your model so you can get the desired output and subsequently achieve your intended business outcome? Do you have access to the data? If so, how much data do you have and where is it? What solution can you use to bring all this data into one centralized repository? The answers to these questions are essential at this stage. The good news for a budding data scientist is that there are many places where you can obtain data. Private data from you or your existing customer already exists, including everything from log files to customer invoice databases. Private data can be useful depending on the problem you're trying to solve. In many cases, private data is found in many different systems. We'll look at how to bring these sources together shortly. Sometimes you want to use data that was collected and made available by a commercial organization. Companies such as Reuters, Change Healthcare, Dun & Bradstreet, and Foursquare maintain databases you can subscribe to. They include curated news stories, anonymized healthcare transactions, global business records, and location data. If you supplement your own data with commercial data, you can get useful insights you wouldn't have gotten otherwise. There are also many open source datasets, ranging from wine quality to movie reviews. These datasets are made available for use in research or for teaching purposes. AWS, Kaggle, and the UCI machine learning repositories are good places to find open source datasets. Government and health organizations are other sources of data that could be useful. Supervised machine learning problems need a lot of data. These are also called observations, and you already need to know the target answer or prediction for that data. This kind of data, where you already know the target answer or prediction, is called labeled data. Each observation in your data is made up of two elements, the target and the features. The target is the answer you want to predict. So in the credit card transaction example, the target of any given observation is either fraud or not fraud. A feature is an attribute of the example that you can use to identify patterns for predicting the target answer. A feature in the credit card example could be the date of the transaction, the vendor, or the amount in dollars of the transaction. You might wonder if the source of the target is fraud or not fraud. Typically, this information is discovered only after the transaction is complete and the actual card owner notices a fraudulent transaction on their statement. This information would be recorded with the transaction for exactly the purpose of using it to train a future model. So given what you know about the elements of an ML dataset, we'll return to one of the original questions. What data do you need to actually train your model to reach the desired output and subsequently your intended business outcome? This is an example of a stage in the ML pipeline when it's crucial to get domain expertise to help you answer this question. With domain knowledge, you can start determining the features and target data your model will need to make accurate predictions. Your data should be representative of the data you'll have when you're using the model to make a prediction. For example, if you want to predict credit card fraud, you need to collect data for positive or fraudulent transactions. You also need to collect data for negative or non-fraudulent transactions. You need both types of data so the machine learning algorithm can find patterns that will distinguish between the two types. Suppose your average amount of fraudulent transactions is actually 3%, but your training data set only includes a very small fraction of fraudulent observations, say 0.4%. In this case, it'll be difficult for your model to truly learn patterns related to fraudulent transactions that it might encounter in production. There are many different services in AWS where you could find or store your data. Here are some key services you might use. Amazon Simple Storage Service is also known as Amazon S3. It provides object-level storage. With S3, you can store as much data as you want in the form of objects, which you can think of as files. They could be CSV files or files of other formats you need. S3 can be accessed through the web-based AWS Management Console. You can also access S3 programmatically through the API and SDKs, or with third-party solutions, which also use the API and SDKs. If your training data is already in S3, and you're planning to run training jobs several times with different algorithms and parameters, you could use Amazon FSx for Lustre. It's a file system service that speeds up your training jobs by serving your S3 data to Amazon SageMaker at high speeds. The first time you run a training job, FSx for Lustre automatically copies data from S3 and makes it available to SageMaker. You can use the same Amazon FSx file system for subsequent iterations of training jobs, which prevents repeated downloads of common S3 objects. Alternatively, your training data might already be in Amazon Elastic File System or Amazon EFS. If so, we recommend using EFS as your data source for training data. It can launch your training jobs directly from the service without needing data movement, which results in faster training start times. This is often the case in environments where data scientists have home directories in Amazon EFS. They can quickly iterate on their models by bringing in new data, sharing data with colleagues, and experimenting with different fields or labels in their dataset. For example, a data scientist can use a Jupyter notebook to do an initial cleansing on a training set and launch a training job from Amazon SageMaker. They could then use their Jupyter notebook to drop a column and relaunch the training job, and finally compare the resulting models to see which one works better. There are many other AWS services and resources where you might find data. For example, you could use Amazon Relational Database Service, or Amazon RDS, a managed relational database service. You could also use Amazon Redshift, which is a managed data warehouse service. Another option is Amazon TimeStream, a managed time series database designed specifically to handle large amounts of data from the Internet of Things, or IoT. You could even spin up your own instances on Amazon Elastic Compute Cloud, which is also known as Amazon EC2, and host your own database on these instances. When you have data sources, you'll need to extract useful data from these sources when assembling your data for machine learning. We'll look at this next. That's it for part 1 of this section. We'll see you again for part 2, where we'll review how to extract, transform, and load data. Hi, welcome back. We'll continue exploring data collection by reviewing how to extract, transform, and load data. Data is typically spread across many different systems and data providers. This presents a challenge. You'll need to bring all these data sources together into something that can be consumed by a machine learning model. You can do this through extract, transform, and load, which is also known as ETL. The steps in ETL are defined this way. In the extract step, you pull the data from the sources to a single location. During extraction, you might need to modify the data, combine matching records, or do other tasks that transform the data. Finally, in the load step, the data is loaded into a repository, such as Amazon S3. A typical ETL framework has several components. As an example, consider the diagram. First, the crawler A program connects to a data store, which can be a source or a target. It progresses through a ranked list of classifiers to determine the schema for your data. Then, it creates metadata tables in the AWS Glue data catalog. A job defines the business logic that's needed to perform ETL work. To run the job, you'll need to use a schedule or event. As a final note, the services we just discussed exist in the transform partition of the ETL process. AWS Glue is a fully managed ETL service that makes it simple and cost-effective to categorize your data, clean it, enrich it, and move it reliably between various data stores. AWS Glue consists of a central metadata repository known as the AWS Glue Data Catalog. This is an ETL engine that automatically generates Python or Scala code. It also provides a flexible scheduler that handles dependency resolution, job monitoring, and retries. AWS Glue is serverless, so you don't need to set up or manage any infrastructure. You can use the AWS Glue console to discover data, transform it, and make it available for search and queries. The console calls the underlying services to orchestrate the work needed to transform your data. You can also use the AWS Glue API operations to interface with the AWS Glue services. This way, you can edit, debug, and test your Python or Scala Apache Spark ETL code using a familiar development environment. AWS Glue is well suited to machine learning because it can receive labeled data that can be used for training. Here's an example. Say that you provide AWS Glue with training data that teaches the model what duplicate records in the data source look like. Then, AWS Glue can identify the duplicates and present them for further analysis by a data engineer. AWS Glue enables the orchestration of complex ETL jobs. In the example, AWS Glue crawls the data sources and presents the information to clients as a data catalog. AWS Glue can run your ETL jobs based on an event, such as getting a new dataset. For example, you can use an AWS Lambda function to trigger your ETL jobs to run as soon as new data becomes available in Amazon S3. You can also register this new dataset in the AWS Glue Data Catalog as part of your ETL jobs. Although managed tools are available in AWS to manipulate data, a data scientist will also write scripts in their Jupyter Notebook to handle data. A very simple extract and load script is shown here. The Imports and Variables section imports the libraries that are used. Note that Boto3 is the library for AWS. Variables are also set here for the zip files web location and a local folder for extraction. The Download and Extract section makes a web request, saving the bytes from the URL as a stream. This stream is passed to the zip file function, which is then used to extract the data. With the extracted files in a folder, the Upload to S3 section enumerates the folder's files and uploads each file to Amazon S3. If you discover that this script is used often, it should be migrated to a standalone function that can be imported by other Python applications. That's it for part 2 of this section. We'll see you again for part 3, where we'll review how to secure your data. Hi, welcome back. We'll continue exploring data collection by reviewing how to secure your data. It's important to consider the security of your data. Though the data sets used in this course are all public, real data about customer transactions or health records need to be kept secure. You can use AWS Identity and Access Management, which is also known as IAM. It's a service that controls access to resources. Make sure you're securing your data within AWS correctly so you can avoid data breaches. The diagram shows a simple IAM policy that allows only read access to a specific S3 bucket for the listed role. In addition to controlling access to data, you need to make sure your data is secure. It's a good practice, and it might also be legally required for certain data types, such as financial data or healthcare records. AWS provides encryption features for storage services, typically for data that's at rest or in transit. You can often meet these encryption requirements by enabling encryption on the object or service you want to protect. For data in transit, you must use secure transports like Secure Sockets Layer, Transport Layer Security, or SSL/TLS. Another aspect to consider is compliance audits. When dealing with data from regulated industries, you'll often need to audit access to the data. AWS CloudTrail is a service that enables governance, compliance, operational auditing, and risk auditing of your AWS account. With CloudTrail, you can log, continuously monitor, and retain account activity related to actions across your entire AWS infrastructure. CloudTrail provides an event history of your AWS account activity, including actions taken through the AWS Management Console, AWS SDKs, command line tools, and other AWS services. This event history simplifies security analysis, resource change tracking, and troubleshooting. You can also use CloudTrail to detect unusual activity in your AWS accounts. All these features can help you simplify operational analysis and troubleshooting. Here are the key takeaways for this section. We looked at the first step in solving machine learning problems, obtaining the data required to train your machine learning model. We also reviewed how ETL can be used to obtain data from multiple sources. Services like AWS Glue can make it easy to obtain data from multiple data stores. Finally, make sure you understand your security requirements. These are based on both business need and any regulatory requirements. Also, make sure your data is secure. Only authorized users should be able to access your data, and it should be encrypted where possible. That's it for section 2. We'll see you in the next video. Hi, and welcome back. This is section 3, and we're going to cover how to evaluate your data. In this section, we'll look at different data formats and types. We'll also look at how you can visualize and analyze the data before feature engineering. Before you can start running statistics on your data to better understand what you're working with, you need to ensure it's in the right format for analysis. For Amazon SageMaker, algorithms support training with data in CSV format. Many of the tools you'll use to explore, visualize, and analyze the data can also read it in CSV format. Generally speaking, you'll need to have at least some domain knowledge for the problem you're trying to solve with machine learning. For example, if you're developing a model to predict if a set of symptoms indicates a disease, you'd need to know the relationship between the symptoms and the disease. Data typically needs to be in numeric form, so machine learning algorithms can use the data to make predictions. We'll look at ways you can convert text data in the next section. For now, we'll just explore the data and try to gain some insights into the overall data set. One popular open source Python library is Pandas. It can take data in various formats, reformat it, and load it into a tabular representation of your data, presenting it in rows and columns. Some of the formats that Pandas can reformat and load include CSV, Excel, Pickle, and JavaScript Object Notation, or JSON. Pandas also has data analysis and manipulation features, and we'll use them throughout this module. Loading data can be as simple as the example, which pulls in the CSV file from the specified URL. When you load data into Pandas, it's stored as a Pandas data frame. In the Pandas documentation, a data frame is described as a general 2D labeled, size mutable tabular structure with potentially heterogeneously typed column. A more helpful way to think of a data frame is to think of it as a spreadsheet or a SQL table. Like a table or spreadsheet, a data frame will have rows, which are also known as instances, and it will have columns, which are also known as attributes. The shape property of a data frame describes the number of rows and columns it has. Each column in a data frame is a series. A series is a one-dimensional labeled array. A series can store data of any type. To learn more about data structures in Pandas, see the Pandas documentation. Along with data, you can load a data frame with row labels and column labels. The row labels are known as an index, and the column labels are known as columns. If you loaded your data from a CSV file with a header row, the columns will be created from the first line of the file. You can change that behavior, however. If you don't have column names in the source file, you can pass them as a parameter. When performing data analysis, it's important to make sure you're using the correct data types. In many cases, Pandas will correctly infer the correct data types when it loads data, and you can move on. If you have domain knowledge or access to a domain expert, they can often identify data type issues. You can use either dtypes or the info function to obtain information on the column types, as shown in the example. If you don't have the correct data types, you need to figure out why this is the case. Often a numeric column could have been missing data, or it could be a single text value. For example, in the car dataset, the number of doors can be 2, 3, 4, or 5 more. After you've analyzed the data, you can convert a column to the correct data type using Pandas. That's it for part 1 of this section. We'll see you again for part 2, where we'll review how to describe your data. Hi, welcome back. We'll continue exploring how to describe your data. Now that your data is in a readable format, you can perform descriptive statistics on the data to better understand it. Descriptive statistics help you gain valuable insights into your data so that you can effectively pre-process the data and prepare it for your ML model. We'll look at how you can do that and discuss why it's so important. First, descriptive statistics can be organized into a few different categories. Overall statistics include the number of rows and the number of columns in your dataset. This information, which relates to the dimensions of your data, is very important. For example, it can indicate that you have too many features, which can lead to high dimensionality and poor model performance. Attribute statistics are another type of descriptive statistic, specifically for numeric attributes. They're used to get a better sense of the shape of your attributes. This includes properties like the mean, standard deviation, variance, and minimum and maximum values. If you need to look at relationships between more than one variable, you can consider multivariate statistics. They mostly relate to the correlations and relationships between your attributes. For cases when you have multiple variables or features, you might want to look at the correlations between them. It's important to identify correlations between attributes because a high correlation between two attributes can sometimes lead to poor model performance. When features are closely correlated and they're all used in the same model to predict the response variable, there could be problems. For example, the model loss might not converge to a minimum state. So be aware of highly correlated features in your dataset. Mean and median are two different measures describing the extent that your data is clustered around some value or position. Mean can be a useful method for understanding your data when the data is symmetrical. However, if your data is skewed or contains outliers, then median tends to provide the better metric for understanding your data as it relates to central tendency. For instance, if you have outliers with large values, the mean can be skewed one way, and it wouldn't serve as an accurate representation of where your values are truly centered. Median isn't affected by outliers in the same way. We'll talk more about outliers soon. Statistics are available, and they can be viewed on numerical data by using methods such as describe. There are also other methods to calculate the mean, median, and others. You can also view statistics on single or multiple columns. You can even group data by specific values. For categorical attributes, you can look at the frequency of attribute values in your dataset. That information will give you some idea about what is inside that categorical variable. The diagram here shows the car dataset, which is made up of several categorical values: buying, maint, lug boot, safety, and class. Safety can be either low, medium, or high. From the describe function, you can see that there are 3 unique values, with low being the most frequent. Looking at the class column, it appears that the top value of the 4 is UNACC, which stands for unaccounted. This accounts for 1,210 of the 1,728 values, or 70%. This might suggest an imbalance. For a target variable that's also of a categorical type, you can look at the class distribution to see whether there's a class imbalance in your dataset. Imbalanced data can mark a disproportionate ratio for your classes. For instance, your dataset is made up of credit card transactions, but only 0.1% is labeled as fraud. In this case, your algorithm might not learn well enough to predict examples of credit card fraud. Visualization could help you gain insights into your data that you might not be aware of otherwise. A histogram is often a good visualization technique for seeing the overall behavior of a particular feature. With a histogram, you can answer questions like, is the feature data normally distributed? How many peaks are there in the data? Is there any skewness for that particular feature? When using histograms for your data visualization, values are binned. The taller peaks of the histogram indicate the most common values. For numerical features, you can use density plots and box plots, in addition to histograms, to get an idea of what's inside that particular feature. Like a histogram, these visualizations will help you answer questions like, what's the range of the data? The peak of the data? Are there any outliers? Are there any special features? Answering these questions helps you understand your data better and can also help you decide if you need to do more specialized data preprocessing. A box plot is a method for graphically depicting groups of numerical data through their quartiles. When you have more than 2 numerical variables in a feature dataset, you might want to look at their relationship. A scatter plot is a good way to identify any special relationships among those variables. In this case, the left diagram has sulfates and alcohol. They are 2 numerical variables. Suppose you want to show the relationship between these variables. You can use a scatter plot to help you visualize that. There are plots scattered around, and the correlation among them might not be that high because the data is scattered. However, you might find some relatively positive relationships between the 2 variables. Scatter plot matrices help you look at the relationship between multiple different features. In Pandas, you can easily create scatter plot matrices based on the columns you want to look at. This example has 3 columns, and it will give the pairwise scatter plot for any 2 columns. With a scatter plot, you might want to identify special regions that a particular subset of data could fit into. In the example, is there a relationship between alcohol sulfates and quality? You could plot those values against good and poor quality wines like the example. Plotting gives you an idea of how useful particular variables can be if you're using them for a classification problem. That's it for part 2 of this section. We'll see you again for part 3, where we'll review correlations and the takeaways for this section. Hi, welcome back. Now we'll review how to find correlations in your dataset. How can you quantify the linear relationship among the variables you're seeing in a scatter plot? A correlation matrix is a good tool in this situation. It conveys both the strong and weak linear relationships among numerical variables. Correlation can go as high as 1 or as low as -1. When the correlation is 1, this means those 2 numerical features are perfectly correlated with each other. It's like saying y is proportional to x. When the correlation of those 2 variables is -1, it's like saying y is proportional to -x. Any linear relationship in between can be quantified by the correlation. So if the correlation is 0, this means there's no linear relationship. But it doesn't mean that there's no relationship. It's just an indication that there's no linear relationship between those 2 variables. However, looking at a number isn't always straightforward. Often it's easier to view the numbers when they're represented by colors. Now we'll look at the heat map. The highest number, 1, in dark green, and -1 is in dark brown. The color gives you both the positive and negative directions, and it also shows how strong the correlations are. We can use the Seaborn heat map function to show the correlation